Hi everyone, my name is Neha and this is the third lecture on Introduction to Automation. In this lecture, we are going to learn about optical rotary encoders. Optical rotary encoders, they produce this angular position data directly in digital form, eliminating any need for the analog to digital converter. So here on the picture, you see a disk which is connected to the shaft, and on the top you see a photocell and a light source. So this a light source and a photocell, they are arranged, their arrangement are mounted so that the slot pass the light beam as the disk rotates. And this information is recorded into the digital circuit which is attached to the photocell. So as the disk rotate, so each rotation, how much angle it has rotated, that information can be fed to the digital circuit which is attached to the photocell. So this optical rotary encoders, they are used in everyday in industrial application, and they provides instantaneous and continuous data on rotation motion. They are designed to monitor speed, position, distance, and direction of rotational movement, and they are used in machines, robots, and elevators, etc. So here we see this example of a robot arm where feedback from the optical rotary encoders can be used to determine the current position of the robotic arm. So using this data, the controller can direct a movement of arm in each of its planes of motion. So here you see these are the angles in degrees: 0, 10, 120 degree, 175 degree, and this is the potentiometer angle which is shown over here: 0, 20, 240 and 350, and this is the pot voltage corresponding to that. So and each potentiometer voltage, if we see the digital value at that particular voltage, then this is the digital value we will get for each voltage. So this basically signifies, for example, if your robotic arm is at 120 degree, then at that point your pot voltage is going to be this and pot angle is going to be this, and corresponding to that the binary state of the robotic arm will be this. So each value of the voltage is basically gives some binary state value, and that we can determine as the robotic arm moves for any angle. Now here, this optical rotary encoders, this is basically of two types: absolute encoders and the incremental encoders. Here you see the absolute optical encoders, and these type of encoders, they are capable of monitoring distance, speed, direction, and absolute position. In this, series of tracks are there, and each track produces 1 bit, and if you have 12-bit encoder, and then that will produce 12 individual tracks. And if you see here, we have 16-bit encoder, and each of them is producing 16 individual tracks, and each of the track has different binary state. If you see here at the top, you see is your LSB, least significant bit, and at the bottom is your mean significant bit. So here you can see, for example, for a 0 track, it will be 0, 0, 0, 0, whereas for track 1, the binary state will be 0, 0, 0, 1, and same with 2 also, 0, 0, 1, 0, and so on. So at the 16th track, it's going to be 1, 1, 1, 1. Now let's see how to calculate the resolution, and the resolution can be calculated by dividing the total angle by the sectors. So here in this case we have 16 sectors, so if we divide 16 sectors by 360, then we will get 22.5 degree. And if you want to increase the resolution of the optical encoders, then you can add more tracks to the encoder, and that will give better resolution. Now let's see, if you have 8 tracks which provides 256 states, then that will yield 360 divided by 256, it will give 1.4 degree per state. And if you have 10 tracks, you know that this will provide 1024 states, which yields to 0.35 degree per states. The same you can calculate for 16 tracks. So this one has the 16 tracks, and if you see, then the states for 16 tracks is going to be more than this, and the state resolution is so much better than what we see over here. Now next is incremental optical encoders, and this incremental optical encoder you see here in the figure, it has only one track of equally spaced slots, and it uses a pulse disk that consists of a evenly spaced clear and opaque segments. And here you see this pulse per revolution. This defines the number of clear and opaque lines on the disk. So for example, if the incremental encoder with a resolution of 200 ppr, then that would give 200 distinct lines on the disk. So this type of optical encoder, it provides speed and directional data to a monitoring and control device. And through the photosensor position, it determines where each slot represents a known angle. Now you see we have two sensors, a position sensor and the reference sensor, and two light sources you see, which will incident the light on each sensors. So in this, if you want to measure the direction, then you will check for the channel, and whichever arrives the first, that will show the direction of the disk. And that information, like whichever the segment comes the first, that information goes into the controller, and the controller it verifies whether the encoder is turning clockwise or in anti-clockwise direction. Now here we have this problem. An incremental encoder has 360 slots, and starting from the reference point, the photosensor counts 120 slot clockwise and 45 slots counterclockwise, and then 35 slots clockwise. So what is the current position of the incremental encoder? So this you can calculate by using this formula. So you know that 120 slot is clockwise first, and then it is anti-clockwise or counterclockwise by 45 slots. So you will subtract it by this, and then you will get 75 which will be in the clockwise direction. And then later it says 35 slots are added in the clockwise direction. So 75 in clockwise direction plus 35 in clockwise direction. Then in total you will get 110 in clockwise direction. So 110 in clockwise direction is the answer. So this is the end of the lecture. Thank you so much for watching.